In this video, we will be discussing the steps of the scientific method and how this process is used to create conclusions or theories about a particular problem or question. All science really is the curiosity of individuals who want to solve a problem. The way they go about solving that problem is by observing and measuring data to formulate an answer to that particular question. So let's start going over the steps of the scientific method in order. And the first step is to make observations and state the actual problem. This problem could also be a question. In order to have an experimental design or experimental steps, you must have a problem or question that you want to solve. The second step is to make predictions and form a hypothesis. Hypothesis is a possible answer to a question, and it must be formulated as an if-then statement. So I could use the example of, if I want my plant to grow, then I have to leave it in sunlight. That if-then statement makes that a hypothesis. It's also your possible solution to a question that you may have about that particular plant. The third step is to test your hypothesis or design your experiment. So when designing an experiment, you have to have two groups in order for this experiment to be considered controlled. You have to have a control group and you must have an experimental group. The control group is used as a comparison. You don't change any variables in the control group. The experimental group will only contain one variable. It's important that there's only one variable that's changed, otherwise it's going to be impossible for you to know what actually made the experimental groups change. As stated before, you can only change one factor or variable at a time. The reason for this is because if you want to find something out, let's just say you want to know what makes plants grow. So you have a control group with, two plants, and you have them in sunlight and you're watering them every day. And then you have your experimental group where, let's just say, you can have more than one experimental group at a time if you're measuring two variables. You would only have one if you're measuring one variable. So because we have two factors here, sunlight and water, you would have one experimental group where you leave the plants in the sunlight but don't water them, and then you could have a second experimental group, or you just do a completely separate experiment where you would have the plants in the darkness, but then you would be watering them. Now, if you were to do both of them at the same time, where you would leave the plants in the dark and you weren't watering them, you really wouldn't know what made the plants not grow. Was it the lack of sunlight, or was it the lack of water? So in order to, know exactly what variable is making a change on your experimental group, you can only change one variable at a time. It's very, very important that you remember that. The purpose of a control group is only used as comparison. You are not testing a control group and you're not experimenting on a control group either. So let's just take the example that I was using about the plants. Let's just say your experimental group was to test the effect of sunlight on plants. So your experiment would be to have the control group. You would have a set of plants in the sunlight and you would be watering them. And then for your experimental group, you would have a set of plants in darkness, but you would still be watering them as well. Remember to eliminate only one variable being changed at a time. Now, obviously, we all know that if you're going to leave a plant in darkness for a certain amount of time, it's not going to grow, no matter how much water you have, that you're going to be watering that plant. In order to compare what would have happened, you have to look at your control group. You're leaving these plants in their control group in the sunlight and you're watering them. Again, we all know this is a very easy example. We all know what's going to happen if you leave plants in sunlight and you water them. They're going to flourish. They're going to grow. But just for the sake of an example, you would use the control group to say, okay, well, I watered it and I left it in sunlight. But again, you're only measuring sunlight, so that's the only variable that counts. So you say, okay, the control group was left in sunlight. The experimental group was not. The experimental group did not grow, where the control group did. So now I have a comparison. Okay, well, sunlight must attribute to plant growth. So that's the purpose of a control. As stated before, a variable is a factor that's being tested in an experiment. And as I said before, a good experiment has two groups, your experimental and your control, and only one variable being changed at a time. Again, the reason for that is because if you want to watch change, the whole point of designing your experiment is to watch change. You have to know what caused the change. And if you're changing too many variables, you're not going to know what actually caused the change. But of course, there are two types of variables, which we're going to get into right now. We have independent and dependent variables. Our independent variable is going to be the variable that we are going to manipulate on purpose. We are changing the independent variable. So in the example of the plant in the sunlight, you would be manipulating the plant by taking it out of the sunlight and putting it in a dark space. So eliminating sunlight would be an independent variable. Your dependent variable is going to be the variable that depends on the manipulation of the independent. So the word independent, let's just take apart this, for a little bit. The word independent means, standing on its own. So we are the ones that are changing on purpose this variable in order to see what's going to happen. That's where the dependent comes in. The what's going to happen part is the dependent variable. So that would be the plant not growing is the dependent variable in that particular example. When someone is independent on someone else, they lean on them, they depend on them. So whatever we do to the independent variable will make the dependent variable change from whatever happens up here. Let me give you another example of how the independent variable and the dependent variable work together. Let me start off with a hypothesis. If I change the type of fertilizer on my plants to type X, we're just going to call it type X just as an example, then they will grow more. So that's my hypothesis. I want to see if changing the fertilizer on my plants is going to make it grow more. So I would make a control group of using the regular fertilizer. I put the plants in sunlight, I would water them, and I would use regular fertilizer. For my experimental group, I would use the new fertilizer, but I would keep them in the sun and I would water them as well. And during my experiment, I would gather data and I would look to see at the plant growth in comparison from control to experimental. Now, in this case, what's my independent variable? What's my dependent variable? Let's start off with the independent. That's always a little bit easier to figure out because you're the one manipulating the independent. So in this case, what are we actually manipulating? Well, the independent variable would be the type of new fertilizer. That would be type X. We are manipulating the type of fertilizer. The control group had the regular. The experimental group is going to have type X. So the answer would be, for the independent variable in this particular experiment, it would be new fertilizer type X. Now from that, what would be the dependent variable? What's going to happen as a result from changing the independent or from changing the fertilizer? Well, the answer would be the plant growth, right? What are we actually measuring, right? This is going to be our measuring variable. What are we actually measuring? We're measuring plant growth. So in this particular case, the independent variable would be the type of fertilizer, and the dependent variable would be the amount of plant growth. Let's take this hypothesis as another example. If high school seniors participate in an intensive study program, then there will be a statistically significant difference in graduation rates. So here is our if-then statement. This is our hypothesis. This is our educated guess, right? Within a hypothesis, there's always going to be an independent variable and a dependent variable, and you need to figure out which one depends on the other. And sometimes even asking yourself that once you figure out which of the two variables there are, it may make it a lot easier for you to go, okay, well, does this depend on this or does this depend on this? And switch them around and see which one actually makes sense. Okay, but remember, the independent variable is the one that we're actually manipulating, and the dependent variable is the one that happens as a result of the independent. So let's just find the two variables, and then we'll give them a name and figure out which one is the independent and the dependent. So we would have as our first one, if high school seniors participate in an intensive study program. Intensive study program. That's going to be one variable right there. Students are being manipulated into taking the study program. This is something that's new. The second variable would be a difference in graduation rates, or just graduation rates as themselves. So we have intensive study program and graduation rates. Those are the two variables that we have. But which one is independent and which one is dependent? Ask yourself the question, does taking a study program depend on the graduation rate, or does the graduation rate depend on if the students take the study program or not? So the second one obviously makes a lot more sense. Therefore, when asking yourself in that way, you've just made the graduation rate the dependent variable and the intensive study program the independent variable. So we are manipulating the intensive study program. This is something that's being, implemented. Students are taking this study program, and what should be the result from the study program? It should be the graduation rate, which is the dependent variable. So as stated before, the independent variable would be the student's participation in the intensive study program, and the dependent variable would be the graduation rates. Step 4 in the scientific method is to record and analyze your data by using charts, graphs, or tables. Now, normally data tables are used while recording the information, while charts and graphs are used to analyze that data. We have two different types of data that we're going to be discussing. There's qualitative data, which is going to be your descriptive type of data. So think of the word quality, the quality of your data. This would be something like colors or sizes or anything really that isn't a number-based data, because that's going to be your quantitative data, which is going to be your numerical data. So think of the word quantity. Quantity is how much. Quality is going to be your descriptive. So an example of quantitative data would be, certain measurements. If you're recording plant growth, you would put the actual measurements. That'd be quantitative. Looking at a certain amount of time, that's numerical based. That would be quantitative as well. Both of them can be used in charts and graphs. They can both be used in data tables. The only difference is that for a qualitative based type of data, you'd probably be using a bar graph. And for quantitative data, you'd be using a line graph or a pie chart. But they can both be made into graphs and they can both be analyzed. So here are two examples of types of data, types of graphs that you could be using for your data. Line graphs and bar graphs. We could also use pie charts when using types of percentages and comparison, which I'll be showing you how to make those in class. We're going to be going over graphing for a couple days, so if this doesn't make sense to you, please ask me in class because we're going to be doing a lot of work on this. But just as an overview, line graphs, okay, they have your y-axis over here. This is going to be where your dependent variable will go. X-axis, this is where your independent variable will be going. And then when using a line graph, you have to have data that shows change over time. So you would have some type of form of time over here, whether it be days, weeks, months, hours, minutes, whatever, seconds, doesn't matter. And then over here, you would have your dependent variable. So what's the change that we're actually measuring? And then here you apply your points and it would show the amount of change. Obviously, this graph is missing a title. Title would go up here. It'd be describing both your y and your x-axis variables in that particular title. But that's really about it. I mean, that's definitely what you would use if you would have any type of data table that shows change over time. That's a line graph, and that's what you would use. Bar graphs, on the other hand, most of the time are used for qualitative data, comparison, anything that's a disconnected group. So you would still have your independent variable down here, but these groups would most likely be disconnected. Maybe you're talking about, you know, the months of the year down here, and then how much rainfall happens in a particular area. Okay, so that's not change over time, that's just comparing between the different months. So that would be considered a disconnected group, and therefore you would not use a line graph because it's not showing change over time, you're just showing comparison. Step 5 in the scientific method would be to form a conclusion based off the data that you recorded and analyzed in step 4. Now, for step 6, you always want to replicate your work. And the reason for that is maybe you just got lucky and your hypothesis matched your conclusion and you just said, okay, that's great, awesome. But what if you just got lucky and it really wasn't the case all the time? So you have to replicate your work in order to ensure that you're going to get the same conclusion over and over and over again. Also, same thing if your hypothesis and your conclusion don't match. You can't just discount it completely because you have to replicate your work and just make sure that there wasn't a fluke. Maybe you made a small, calculation error in your data, which means that, your hypothesis and your conclusion really could have matched, but you just made a small error. So it's always good to go back and replicate your work to make sure that your result really is true before telling the world that you've come up with some type of new idea. A theory is just a hypothesis that has been tested over and over and over again and is yet to be disproven. So remember, as we said, when you have your hypothesis, that's just your educated guess, that's just your if-then statement, and you go through the steps, you design your experiment, you record your data, you analyze your data, you come up with a conclusion, and if your conclusion supports or matches your hypothesis, then you've made a valid hypothesis. Now you have a valid conclusion. But again, as stated before, you must repeat that work in order to ensure that there were no flukes in your data, no mistakes, everything was okay. You have other people test your hypothesis. And until there comes a point where nobody can disprove it, that's when that hypothesis and conclusion becomes a theory. So just to wrap everything up that we've talked about today, remember that questions will always lead to your hypothesis and your predictions. Your hypothesis is going to be your if-then statement. It's going to be your educated guess about your question or problem. From there, you're going to design your experiment, where your experiment will have 2 groups, control group and experimental group, and within those, you're going to have your independent variable and your dependent variable. Some of your hypotheses are going to be supported after reading through and analyzing your data. If your data matches your hypothesis and your hypothesis is supported at that point, if it continues to be verified by a lot of people and it cannot be disproven, it will then turn into a theory. Remember, there's always the other side where Maybe your hypothesis does not match your conclusion. I'm sorry, your hypothesis doesn't match, it doesn't match your conclusion. And your hypothesis would then be considered rejected. That's okay. Most of the time, that's what happens anyway in science. All you have to do is go back, revise your hypothesis, try a new experiment, and continue to work. If at first you don't succeed, you always try again and you create a new hypothesis, because eventually you are going to have a hypothesis that is supported.